Swayam Prabha. Digital India. Educated India.
Welcome back to lecture number 19 on the topic psychrometric processes. Before seeing the contents of today's lecture, this session lecture, let me have a quick recap on what we have discussed in the previous lecture number 18. We have started a new topic, that is the science of psychrometry. So, it is a branch of science which deals with the properties of air and water vapor mixture. Why we need to study the properties of air water vapor mixtures is when air is circulated through the various devices or components in an air handling unit. So, there are a lot of thermodynamic changes which takes place. Suppose if it is if the air is circulated through a preheating coil, the temperature varies. It is like since it is a sensible heating, the temperature at the outlet is more than the temperature at the inlet. Similarly, when it passes through a humidifier, the amount of moisture added at the when the air leaves the humidifier, its moisture content will be more, because in the humidifier the specific humidity amount of moisture, which is in terms of grams or kilograms per kg of dry air, increases. So, as the air leaves the air conditioned space, the return air temperature is higher than the supply air temperature. So, again it has to be recirculated, some amount of fresh air has to be added. So, then the process again continues. So, in order to study the thermodynamic changes that happens when the air is circulated, so there is a necessity to know the psychrometry, to know about the psychrometric chart, what are the various processes. Yesterday we have seen how to evaluate the properties, how to find out the properties using psychrometric chart. If we take the psychrometric chart, on the x-axis we have the dry bulb temperature dBT, y-axis is the specific humidity. Specific humidity is the amount of moisture which is present in kg, in 1 kg of dry air, and there is a scale which is outside the saturation curve, that is the enthalpy scale. If we want to find out the dew point temperature, which is the temperature at which or below which the moisture in the air starts condensing. So, we have to draw a line parallel to the x-axis towards the left until it touches the saturation curve. Then there are lines, two inclined lines, one is wet bulb temperature line and another one is specific volume meter cube per kg. The difference between dry bulb temperature and wet bulb temperature is wet bulb depression. So, we have solved numericals using psychrometric chart as well as empirical relations. In this lecture we will see the various psychrometric processes, and again we will be using the psychrometric chart to solve the problems. Sensible heating, the contents of this today's lecture number 19. Sensible cooling, humidification, dehumidification, heating and humidification, cooling and dehumidification, adiabatic saturation or evaporative cooling, and chemical dehumidification. There are about 8 processes which we will be studying in this lecture. Let me start with the sensible heating process. So, we know the difference between, we are familiar with the difference between the sensible heat and latent heat. Sensible, let me emphasize it again. Sensible heat is the heat which causes the temperature to increase or decrease. If it is heating, the temperature will increase. If it is cooling, the temperature will decrease without any change in the humidity. So, if you see this in every, I will explain each and every process with the help of a psychrometric chart. So, here x-axis is the dry bulb temperature, as we know. The right hand side y-axis, I think there is some initial state. One is the initial state of the process, 2 is the final state of the process. You can see dry bulb temperature 1 corresponding to 1, dry bulb temperature 2 corresponding to. Dry bulb dB2 dB2 is greater than dB1. As we know, the heating process enhances the temperature. Okay, so dry bulb temperature 2 is greater than dry bulb temperature 1. And if you see the line is perpendicular to the y-axis or parallel to x-axis. So the specific humidity remains constant. Specific humidity at 1 is equal to specific humidity at 2. That is, before the air is heated, whatever the specific humidity is there, that will continue to remain if it is a sensible heating process. There will be change only in the temperature. There will be change only in the temperature. So little ago I was recollecting about the sensible heat and latent heat. Sensible heat does not cause the phase change. Latent heat does not change the temperature. Temperature remains the same, but only the phase change from vapor to liquid or liquid to vapor, solid liquid or liquid solid, etc. happens. So this is about sensible heating. So to summarize this process, it is a process during which the temperature of the air increases from state point 1 to state point 2. It can be, it may be from 30 degree to 35 degree or 40 to 50 degree, whatever it is. But the specific humidity or the absolute humidity remains constant, The process which is opposite to sensible heating is sensible cooling, So if sensible heating, obviously the arrow mark will be towards the right side because the x-axis is dry bulb temperature. So at the end of the sensible heating process, the temperature will be more. So obviously the arrow mark should be pointed towards the right side as we move along the x-axis. But for sensible cooling, it is just opposite exactly. State point 1 will be on the right side. Will be on the right side. The air is cooled during this process. The air is cooled from 1 to 2. So the temperature at 1 is more than the temperature at 2, or in other words, temperature at 2 is less than temperature at 1. Here also the specific humidity continue to remain same. So in both sensible heating and sensible cooling, the humidity remains constant. So let me underline this one. So in both sensible heating and sensible cooling, there is no change in specific humidity. Neither the moisture is added nor the moisture is removed from the air. This W value will change only when moisture is removed to the air, from the air, or moisture is added to the air. So these two are the first two processes, sensible heating and sensible cooling. The third process is humidification. Humidification, adding humidity. It is like dehumidification is removal of humidity, removal of moisture. Humidification is addition of moisture. So here it is just only humidification. So there is no change in the dry bulb temperature. So from state point 1, the corresponding specific humidity is W1. At state point 2, after humidification process, it is W2. So in sensible heating, like dry bulb temperature at point 2 is greater than dry bulb temperature at point 1. Similarly here, dry bulb temperature there W remains constant. Here dry bulb temperature remains constant, whereas W2 is greater than W1. W2 is greater than W1. You can see on the right side y-axis, W1 is at the bottom and W2 is at the top. So obviously W2 will be more than W1. Whereas the dry bulb temperature at 1, let me underline this one, here dry bulb temperature at 1 is equal to dry bulb temperature at 2. There is no change in the temperature of the air. There is no heating process. It is only humidification, adding of moisture content to the air. So this difference W2 minus W1 depends upon the amount of moisture that has been added to the air during the humidification process. If more amount of moisture is added, then the difference W2 and W1 will be large. If the amount of moisture which is added to the air is less, then the difference also will be less. So this is the third process, which is the humidification process. Dehumidification process. This is just opposite to humidification process. during this dehumidification process, it is removal of moisture, So, state point 1 will be at the top and 2 will be at the bottom. So, here also dry bulb temperature at 1 will be equal to dry bulb temperature at 2. Dry bulb temperature at 1 will be equal to dry bulb temperature at 2. Here if you see, as the moisture is removed, the specific humidity decreases from W1 to W2. Again here also, here W2 will be less than W1. In the previous one, W2 will be greater than W1. Okay. So, here let me write this one. Here W2 is greater than W1. In this one, the final specific humidity is less than initial specific humidity. Similarly, in the first slide, let me write sensible heating, dry bulb temperature 1. Let me write the higher value first. So, dry bulb temperature at 2 will be greater than dry bulb temperature at state point 1. That is sensible heating. In sensible cooling process, dry bulb temperature at 2 will be less than dry bulb temperature at state point 1. So, if you compare and while you are studying, you compare sensible heating and cooling, it will be easy to understand also. And the process which is opposite to humidification is dehumidification. So, one is addition of moisture, the other one is removal of moisture. So, when moisture is added, the final specific humidity will be more than the initial specific humidity. When moisture is removed, the final specific humidity will be less than the initial specific humidity. So, W2 is less than W1. So, now we have seen 4 processes, psychrometric process out of 8. Let us see the 5th process. So, it is a combination of process 1 and 3. First, process 1 is sensible heating, third process is humidification. So, it is a combination of process the first and third, heating and humidification. So, when I say heating, obviously the temperature will increase. When a process involves humidification, specific humidity also will increase. So, the line cannot be parallel to x axis or perpendicular to x axis or parallel to y axis. So, it cannot be, because if the line is either parallel to x axis or parallel to y axis, that means one property remains constant. So, which is not possible in this case of heating and humidification process. So, it has to be an inclined line. It can be an inclined line like this with an arrow. So, that is what I have mentioned in the next process. So, here you can see when heating causes the temperature to increase, humidification causes the amount of moisture that is present in the air will increase. So, here dry bulb, both the condition of the air at the outlet, both dry bulb temperature and specific humidity will be more than the initial state. So, dry bulb temperature 2 is greater than dry bulb temperature 1 and specific humidity also is greater than initial state. So, both the properties at the final state, that is specific humidity and the temperature, is greater than these respective properties when we compare to the initial state. So, the arrow mark should be pointed towards upward. See, arrow marks are very, very important. Any process without arrow mark is meaningless, first of all. If we do not mark the direction properly, then the process name itself will change. For example, when we say it is an isentropic process, isentropic compression means the arrow mark should be pointed towards state point 2 from 1 to 2. When we say expansion, it will also be pointed towards state point 2, but it is in the downward direction. So, compression is always we express the process, the arrow mark in the upward direction. The expansion process arrow marks are representing the downward directions. So, similarly here heating, when I say heating, here it is an inclined curve which is pointed towards upward, in the upward direction. So, when the next process is cooling and dehumidification. So, the arrow mark, the process will be the line, if you compare the trend of the curve, it will be similar only, but the arrow marks will be in the opposite direction. So, this is about heating and humidification process, where the temperature of the air at state point 2 and the humidity of the air at state point 2 is more than the initial state. Cooling and dehumidification. It is a combination of process 2 and process 4. Second process is sensible cooling, and fourth process which you have seen is dehumidification. Cooling reduces the temperature of the air. So, the initial temperature will be more, final temperature will be less, or the final temperature is less than the initial temperature. Similarly, the amount of the moisture is removed from the air. Some amount of moisture is removed from the air. So, the humidity also comes down. So, cooling and dehumidification is the temperature also reduces and the specific humidity also reduces. So, here it is just opposite to heating and humidification. W2 is less than W1 and dry bulb temperature at point 2 will be less than dry bulb temperature at point number 1. So, both the properties, dry bulb temperature and specific humidity or absolute humidity at the final state will be less than the respective properties at the initial state. So, this is cooling and dehumidification. So, we have covered 6 processes. First is sensible heating, second one is sensible cooling, then humidification, fourth one is dehumidification, fifth one is the combination of process 1 and 3, heating and humidification, and the process which you have seen just now is the combination of process 2 and process 4, which is cooling and dehumidification. Let us move to the 7th process. It is called the adiabatic saturation or evaporative cooling. Evaporative cooling used in the cooling towers, all those things and all, where normally in the cooling tower what happens, the condenser water, the water after cooling the condenser, the temperature of the water is more, so it is sent back to the cooling tower, where it is cooled by the air, and the air picks up the heat from the returning water from the condenser, it cools the inlet water supplied to the condenser, again the water is circulated back. So, here during this process the enthalpy remains constant. During this process the enthalpy remains constant, which is entirely different from all the previous processes. So, here this is the saturation line, this is the saturation line, this is dry bulb temperature 1, this is dry bulb temperature 2. As I said, it involves cooling. So, the temperature will be less, the exit temperature will be, the temperature of the air after the process will be less. So, initial temperature is 1, dry bulb temperature 1 and dry bulb temperature 2. So, dry bulb temperature 2 is less than dry bulb temperature 1, but W2 is not less than W1, W2 is more. So, here that means the temperature is reduced, little amount of moisture is this one added. So, amount of moisture which is added to the air increases. So, W2 is greater than W1. So, during this process enthalpy remains constant. So, you can see this is, suppose if I extend this line, the enthalpy scale is outside the saturation curve. So, enthalpy at 1 is equal to enthalpy at 2. So, let me write that one, enthalpy at 1 is equal to enthalpy at 2. So, this is adiabatic saturation or evaporative cooling, because the air is used to cool the water. So, as it removes this one, so the moisture content of the air increases, or in other words, the adiabatic saturation, it is also called as adiabatic saturation, like the air is cooled, the latent heat, the sensible for phase change process we need a latent heat. So, that is taken from the air. So, the air gets cooled, and in the process when the moisture is added to the air, the specific humidity increases. Chemical dehumidification. So, this is opposite to adiabatic saturation or evaporative cooling. So, here if you see, here also the enthalpy remains constant. So, H1 is equal to, if I extend this line, if I draw the line parallel to wet bulb temperature line, yesterday I have told very clearly, if you want to find out the enthalpy from the point, once you know the condition of air either at the inlet or outlet, we can find out the enthalpy corresponding to that point. The line which you are drawing from that point should be parallel to wet bulb temperature line, So, here also it is H1 is equal to H2, H1 is equal to H2. So, dehumidification, we know the meaning of the word dehumidification, removal of moisture. So, W2 is less than W1, but dry bulb temperature at 2 is greater than dry bulb temperature at 1, dry bulb temperature. So, this is done by using some chemicals. So, that is why it is called chemical dehumidification. Some chemicals are used to achieve this process. Okay. So, let us compare the previous. In evaporative cooling, if you see the difference between evaporative cooling and chemical dehumidification, in evaporative cooling, the specific humidity of the air, conditioned air is more, that is W2 is greater than W1. In chemical dehumidification, since it is removal of moisture, W2 is less than W1. In evaporative cooling, the dry bulb temperature, the outlet dry bulb temperature is less than the inlet, because the air is cooled, and this one, in case of chemical dehumidification, the dry bulb temperature of the air at the outlet, at the exit of the device is more than the inlet dry bulb temperature. Enthalpy remains constant in both the cases. So, this schematic shows the summary of all the processes, all the 8 processes which we have discussed. Sensible cooling, you can see this is process 1 is sensible cooling, sensible heating, 1 is sensible heating. So, let me write the process. 1 is here, 1 is sensible heating, where you can see the process 1, where the temperature will increase, there is no change in humidity, the humidity remains constant. So, this is like a wheel, 2 is opposite to 1, sensible cooling, this is 2 is sensible cooling. Okay. 3 is humidification. If you see the line perpendicular to x axis, so it could be humidification, where the temperature remains constant, the specific humidity increases. Humidification. Four is opposite to humidification, that is dehumidification. So, 1, 2, 3, 4. Okay. Then 5 is heating and humidification. Let me write it here. 5 is heating and humidification. And 6 is just opposite to 5, that means cooling and dehumidification. 7 is adiabatic saturation or evaporative cooling. Evaporative. And 8 is just opposite to 7, which is chemical dehumidification. Chemical let me write capital letter D. So, chemical dehumidification. So, it is like a wheel. So, where we can represent all the process, 8 processes which you have seen. Okay. So, now I have prepared a table comparing all the 8 processes, which are all the property changes. The green color represents increase in that particular property. Wherever I have mentioned green color, that means that property increases. Blue color is the property decreases, blue color is decreases, and the sandal color is neither the property is increasing nor decreasing, neither increasing nor decreasing. Sensible heating process, dry bulb temperature increases, the wet bulb temperature also will increase. Dew point temperature remains constant. So, if we extend the line, process line 1 to 2 towards the left side, there will be only 1 point, so it is constant. Specific humidity remains constant, relative humidity decreases, and enthalpy increases, because dry bulb temperature at 2 is more than 1. So, enthalpy is increasing. Sensible cooling, dry bulb and wet bulb is just opposite, decreases. Dew point and specific humidity remains constant. Relative humidity increases, just opposite to sensible heating process, and enthalpy will decrease, because dry bulb temperature at 2 will be less than dry bulb temperature at 1. Humidification, in humidification the dry bulb temperature remains constant, so because the line is perpendicular to y axis. If you see this one, this is humidification, and dehumidification also dry bulb temperature remains constant. So, in both humidification and dehumidification, the dry bulb temperature remains constant. Okay. In case of humidification, wet bulb increases, dew point increases, specific humidity increases, relative humidity increases, and enthalpy will increase. Because the state point 2, see, if you see the humidification process, let me explain this one. See here, see when we plot the enthalpy when I find the enthalpy at state point 2 and 2.2 is at above 1. So, enthalpy at this point will be more than enthalpy at this point. That is, humidity is added. So, yesterday I have told in one of the slides, in one of the lecture, that there are 2 components of air. One is sensible heat, that is due to the temperature. The other one is the latent heat, due to the humidity. So, dehumidification, the dry bulb temperature remains constant, and exactly opposite to humidification, where wet bulb, dew point, W is the specific humidity, phi is the relative humidity, and enthalpy decreases, just exactly opposite to humidification. Next one, heating and humidification. Heating increases the dry bulb temperature, wet bulb temperature, dew point temperature, specific humidity, because humidification is adding of moisture to the air, relative humidity and enthalpy. Cooling and dehumidification, all the properties decreases. Dry bulb temperature, wet bulb temperature, dew point temperature, specific humidity, relative humidity and enthalpy. Adiabatic saturation, dry bulb temperature decreases. Okay, so you can see here, this is adiabatic saturation. Okay, other name for adiabatic saturation process is evaporative cooling process. Okay. Wet bulb remains constant, dew point, specific humidity, relative humidity increases, and enthalpy also remains constant, because here you can see the curve, H1 is equal to H2, whereas specific humidity is more. If this is more, RH will be more, relative humidity will be more, but H1 equal to H2. Dry bulb temperature 2 is less than dry bulb temperature 1. So, adiabatic saturation is the other name for evaporative cooling. Then the last process which you have seen is chemical dehumidification, which is just opposite to the previous process. Dry bulb temperature increases, wet bulb remains constant, enthalpy remains constant. Here also enthalpy is constant. So, this is chemical dehumidification. H1 is equal to H2. H1 is equal to, let me underline this one, H1 is equal to H2 in both evaporative cooling and chemical dehumidification process. See, in evaporative cooling process, that is it is between water and air. Okay. Whereas in case of chemical dehumidification, it is done by using some chemicals, as I said before. So, in chemical dehumidification, the dew point, specific humidity and relative humidity decreases. Blue color indicates the property decreases, green color indicates the property increases, and the sandal color indicates the property remains constant. So, I have given the legend in the previous slide. So, due to space constraint in this one, so I have not just mentioned, but the same colors have been used. So, with this background, let us solve some numericals. So, I would be explaining 4 numerical questions, 4 different processes. Of course, the psychrometric chart is already in the previous lecture I have explained how to see the properties, like the enthalpy scale is outside the saturation curve, right side y axis is the specific humidity, x axis is the dry bulb temperature, saturation curve to be used if you want to find out dew point temperature, and the inclined and the curves are there are only if you see the psychrometric chart, constant curved lines are there which indicates the values of various relative humidity, phi value in terms of percentage, which can be easily identified because that is the only property which is expressed in terms of percentage. And there are other 2 inclined lines, one is specific volume lines in meter cube per kg and another one is wet bulb temperature line in degree centigrade. Atmospheric air at a flow rate of 3 kg per second, mass flow rate is given, enters a cooling and dehumidifying coil. So, it is a cooling and dehumidification process, with an enthalpy is given 85 kilojoule per kg of dryer and a humidity ratio. Humidity ratio is nothing but specific humidity. It is the condition of the air at the inlet is given. It is enters a cooling and dehumidifying coil. At the entry point, the enthalpy of the air is 85 kilojoule per kg and the humidity ratio is 19 grams of moisture in 1 kg of dry air. The air leaves the coil with an enthalpy. So, the enthalpy of the air after the air is conditioned, after the process is given as 43 kilojoule per kg and a humidity ratio is given. If the condensate water leaves the coil with an enthalpy of 67 kilojoule per kg, determine the cooling capacity of the coil. So, I have transform the given numerical question in the form of a schematic, in the form of a process. So, here we have, this is the mass flow rate of the air is given, inlet enthalpy is given, inlet specific humidity, that is the humidity ratio is given W1, okay. Enthalpy at state point 2 is given, that is at the exit, and at the outlet or the exit the specific humidity is given. So, this is outlet and this is at the inlet, okay. And whatever the condensate that has been collected during this process, that also we have to find out the cooling capacity of the coil. The condensate water leaves the coil with an enthalpy of 67. So, there is that so much amount of heat is removed. So, that's why the arrow mark is this one, and this is the heat is removed. It is a cooling and dehumidification, that is the temperature drops, that is why there is a drop in enthalpy. Inlet enthalpy is 85, outlet enthalpy is 47, and also there will be dehumidification is removal of moisture, So, W2 will be less than W1. See here, the inlet specific humidity is 0.019 kg per kg of dry air, okay. The inlet specific humidity is also given in grams, this is in grams, okay. So, this is in grams and this is also in grams, humidity is given in terms of grams. So, we have to convert it into kilogram, So, divide by 1000. So, I have given this is the mass flow rate, it is not mass, the dot is missing. So, m dot A is equal to 3 kg per second, enthalpy at inlet, specific humidity at inlet, enthalpy at outlet, specific humidity at outlet is given, okay. So, we can apply the mass balance, okay. So, see here if you see, this is apply the mass balance for this one, m dot A into W1 equal to m dot A into W2 into that condensate, okay. So, I am finding the how much water is collected per second, So, apply the mass balance. So, mass balance, quantity of air flowing into the specific humidity at 1 is equal to m dot A into W2 plus the amount of water condensate collected. So, if you see this one, so m dot W we can find it out using this the only unknown is this is given W1 W2 is given, W1 is 0.018, this is given m dot A is given as 3 kg per second, W1 is 19 grams 0.019 kg per kg of dry air, specific humidity 2 is equal to 8 grams 0.008 kg per kg of dry air. Let me emphasize again, the numerator kg is the kg of moisture, denominator kg is the amount of dry air. So, this is given m dot A, you know, the only unknown is m dot W. So, substitute and find out the value as, so if you see the 0.033 kg per second, 0.033 kg per second, 0.033 kilograms per second. Okay. Now, apply the energy balance for this equation, energy balance equation. So, if you see there are 4 arrow marks here, one is for the inlet, one is for the outlet, condensate and the amount of heat removed, that is how much heat is removed from the air by the cooling coil, because the air is cooled, So, there are 4 arrow marks. So, 2 are, see if you see only this arrow is pointed towards the inside, it is entering in, okay, whereas the other 3 arrows are, it is away from the system, that is pointed towards outside. So, m dot A, when we write the energy balance, we have to bring enthalpy, okay. So, m dot A into H1, that is what I wrote, m dot A into H1. So, this is the inlet equal to, there are 3 arrow marks which are pointing outwards, one is Q, one is the condensate, how much this one, and one is the enthalpy, the quantity of air which is leaving the process after the process is completed with a particular enthalpy. So, let me put dot here. So, let me draw the diagram simply, this is inlet, this is outlet, inlet is state point 1, outlet is state point 2, then the cooling coil removes the heat, then condensate HFG. Okay. So, these 3, only this arrow is, this is into the system, whereas the other 3 are leaving the system. So, energy balance is this energy is equal to the summation of these 3. So, energy balance m dot A into the enthalpy at 1 is equal to this mass into enthalpy plus this mass, this quantity, of course, this here directly we have to find out, this is the capacity of the cooling coil, how much heat has been removed by the coil from the air, and this is given. So, m dot A into H2, that is enthalpy of the air leaving this one, plus Q plus the condensate m dot W into HFG. This is the condensate. So, the only unknown is this one. So, we know all these values. Okay, m dot W just now we have found out using mass balance, So, substitute all the values, you will get the capacity of the cooling coil as 124, if we round off, Q is equal to 123.8, and these are all the given conditions, these are all the given data. So, enthalpy at 1, let me write the given data also, enthalpy at 1 is 85 and enthalpy at 2 is 43, 85 kilojoule per kg and H2 is equal to 43 kilojoule per. Okay, so, substitute everything, enthalpy is in kilojoule per kg and the flow rate is in mass flow rate of the air, and water it is in kg per second. So, kilojoule per kg into kg per second, kilogram and kilogram will get cancelled and you will get kilojoules per second, which is kilowatts. So that completes the problem. It is a very practical problem which I have taken. So this is without using the psychrometric chart, because these values are given. So directly this enthalpy value is given at inlet and outlet, specific humidity is given at the inlet and outlet. If you otherwise, if you know the temperature, we can find out the properties from the psychrometric chart. Psychrometric chart. Here at atmospheric pressure at a dry bulb temperature of 40 and a wet bulb temperature of 20. So dBT and WBT are given. It is humidified in an air washer operating with continuous water circulation. The wet bulb depression at the exit. Let me recollect what is meant by wet bulb depression. It is the difference between dry bulb temperature and wet bulb temperature. If wet bulb depression is 0, that means both dry bulb and wet bulb are same. If dry bulb and wet bulb temperature are equal, then wet bulb depression is equal to 0. The wet bulb depression at the exit is 25% of that at the inlet. Calculate the dry bulb temperature at the exit of the air washer. Okay. So you can use dBT or WBT. Okay. So for the inlet, we always use state point 1, and for the outlet it is state point 2. And if it is more than, if it is like a mixing process where one air stream mixes with another air stream, so there will be multiple state points. So dry bulb temperature 1 is given as 40 degrees centigrade. Wet bulb temperature at 1, both the temperatures are given at the inlet, that is 20 degrees centigrade. 20 degree centigrade. Or this is equal to, you can write like this also, dry bulb temperature, wet bulb temperature. Wet bulb depression, wet bulb depression, wet bulb depression, WBD. It is the difference between dry bulb temperature and wet bulb temperature. Because dry bulb temperature cannot be less than wet bulb temperature, so the first term should be the dry bulb temperature minus wet bulb temperature. Okay. So here both these are given, dry bulb and wet bulb. So in this case it is 40 minus 20, 20 degrees centigrade, wet bulb depression. Okay. Let me put a comma and write. So the short form which is used is WBD. So wet bulb depression. So this is the difference between dry bulb temperature and wet bulb temperature. So that's what I have found here. Now it is given, one more data is given, the wet bulb depression at the exit. Wet bulb depression at the exit. Since there are two wet bulb depression, inlet and outlet, so I will use wet bulb depression at inlet. This is the one which we have calculated is the wet bulb depression at inlet. So that means WBD1, dry bulb temperature 1, wet bulb temperature 1. Okay. So this is dry bulb temperature 1, wet bulb temperature 1. So I am using WBD1 to represent the wet bulb temperature at state point at inlet condition. Okay. So inlet is 1. So let me write it. Inlet is state 1, state point state 1, and outlet is state 2. Outlet is state 2. Now it is given as the wet bulb depression at the exit is 25% of the wet bulb depression at the inlet. It is given that wet bulb, let me write, it is given that wet bulb depression at exit or outlet is equal to wet bulb depression
at inlet, it is some amount, that is 25%, it is equal to 25%. So, let me write it neatly, otherwise later when you refer it will be easy. Without reading the problem you can understand. It is equal to 25% of wet bulb depression at inlet. This is given in the question. Okay. So, let me underline this sentence alone, at the exit is equal to 25% of that at the inlet. Okay. So, now wet bulb, convert this statement into the formula. Wet bulb depression at outlet is WBD2 is equal to 25% of wet bulb depression at inlet. So, this is equal to 25 by 100 into the wet bulb depression at inlet. This is what? WBD2. Now, 25, the right side we know, that is 0.25 into wet bulb depression at inlet. This is the wet bulb depression at inlet. For given dry bulb temperature 40 degree minus wet bulb temperature 20 degree. So, 40 minus 20. So, this is 20. So, this is 1/4 of 20, which is equal to 5 degree wet bulb depression. Now, I have found the wet bulb depression at the exit, at the outlet, for the outlet. Okay. Now, here it is given us at a dry bulb temperature of given dry bulb temperature, by using this we can find wet bulb depression 1. Then using this the second statement, wet bulb depression 2 is equal to 25% of wet bulb depression 1. Okay. So, now I have found this one. So, which is 5. This is what here. This is what 5. Now, you are asked to find out the dry bulb temperature 2. Okay. So, use this formula, wet bulb depression 2 is equal to dry bulb temperature at 2 minus wet bulb temperature at 2. So, this we can write wet bulb, because it is the difference between dry bulb temperature and wet bulb temperature. Now, I have written that one for state 2, that is for the outlet condition. Now, this is known, we have to find out this, Therefore, dry bulb temperature at 2 is equal to wet bulb depression at 2 plus wet bulb temperature 2. Okay. Now, for this process, the wet bulb temperature is same. For this, same for the process which is given, there is no change in the wet bulb temperature. So, this is 5 degree centigrade, and wet bulb temperature 2 is nothing but wet bulb temperature 1. Wet bulb temperature 1 is given as 20. So, the dry bulb temperature of the air at the exit of the air washer is 25 degree centigrade. So, that completes the problem. Okay. So, this is, since this is WPT1 is equal to WBT2 for a process in an air washer, the specific humidity remains same. The wet bulb temperature remains the same, not the specific humidity, the wet bulb temperature remains the same. So, this is for a air washer. The wet bulb temperature of the air at the inlet and the outlet remains same. Now, let us move to the third question. 25 kg of air at 25 degree centigrade dry bulb temperature and 65% relative humidity is mixed with 5 kg of air at 5 degree centigrade dry bulb temperature and 30. So, there are two air streams given. Okay. So, we have not seen the psychrometric process, which is the related to mixing of air stream. So, we have seen 8 processes: sensible heating, sensible cooling, humidification, dehumidification, sensible heating and humidification, sensible cooling and dehumidification, evaporative cooling and chemical dehumidification. And this is the 9th process, Okay. So, I have not shown this one on in that summary of processes. So, here as you know, the dry bulb temperature is here, wet bulb the specific humidity on the right side. There are two air streams. Let me plot this in the form of a diagram. It is like this. One air stream is coming like this, state point 1, another air stream is coming like this. So, both are mixing and you get another air stream. Okay. So, these two air streams combined we will get. So, there will be 3 state points. One state point represents one air stream, the other state point represents the second air stream. Both are combining, both are mixing and leaving coming out of the process after the mixing process. So, that is this one. So, this is stream 1, this is stream 1, this is stream 2. Okay. So, see here it is kg. So, it should be written as m only, not flow rate is given. Only if flow rate is given you have to write m dot. M1 is given as 25 kg, stream 1 data is given, M1 is equal to 25 kg. Okay. Dry bulb temperature 1 is equal to 25 and phi 1 is 65, 25 degrees centigrade, phi 1 is equal to, relative humidity is given. So, that is expressed in terms of percentage. So, for this stream, okay, mass is given, dry bulb temperature is given and relative humidity is given. Similarly, for this stream, mass is given, dry bulb temperature, let me write M1 dBT1 phi 1, dBT2 phi 2, all the 3 parameters properties are given. So, M2 is 5 kg, dry bulb temperature 2, stream 2, M2 equal to 5 kg, dry bulb temperature 2 is equal to 5 degrees centigrade and relative humidity is equal to, let me check how much it is given, it is 30%. Okay, let me quickly finish this one. Okay. So, already we have taught you how to use the psychrometric chart. We know 2 properties apart from the mass flow mass, we know 2 properties. So, using these 2 properties, okay, at dry bulb temperature 1 equal to 25 degrees centigrade and phi 1 is equal to 60. So, we can find out the condition of air on the psychrometric chart on this. So, this is the psychrometric chart. Okay. Okay. So, suppose and enthalpy scale are like this. Okay, I think let me this is the diagram. So, this is the condition of the air at the stream 1, this is stream 1, this is stream 2, this is point 3 represents the after the air is mixed, that is stream 3, So, I can fix this point because I know the dry bulb temperature and relative humidity. I can using the dry bulb temperature 2 and relative humidity at 2, I can find out state point 2. So, draw the line parallel to, these lines should be drawn parallel to wet bulb temperature lines. Let me again remind you all. Okay. So, the enthalpy at 1 is 52, enthalpy at 2 is 10. So, from psychrometric chart, So, you can find out enthalpy at 1, that is 52 and the enthalpy at 2 is 10, 52 kilojoule per kg, and similarly at dry bulb temperature 2 is equal to 5 degrees centigrade, relative humidity is equal to 30%. Okay. We can find H2 is equal to 10 kilojoule per kg. So, that is what I have done here using. Now, mass balance. What is the mass balance? Okay. If you see this diagram, this 2 streams are entering. So, M1 plus M2 will be equal to M3, M1 plus M2 equal to M1 plus M2 is equal to M3. This is given, so we can find out M3. M3 is equal to 25 plus 5, 30 kg, 30 kg. So, that is what I have found here, mass at 3, and find out the energy balance. How to write the energy balance for this stream? M1H1 is the energy of this stream, and this one M2H2, these two will be equal to M3H3. Okay. So, write the energy balance. We can, using mass balance you can find M3, using energy balance we can find H3, and from this, from the psychrometric chart. So, now you know the at state 3. So, you can fix this point, you can fix this point from so we know H1 and H2, so we can fix this one. So, now this is known, this is known. So, once you fix this one, draw a line parallel to wet bulb temperature line that will intersect this process line 1 to 2. That intersection point is 0.3, that intersection point is 0.3. Read the value of dry bulb temperature and humidity at that point. So, there is one more question which I have given. So, due to shortage of time, I am not able to explain. In case if there is some time in the subsequent lecture, I will be able to explain this one. So, to summarize, we have seen the various psychrometric processes in this lecture: sensible heating, sensible cooling, humidification, dehumidification, then a combination of sensible heating and humidification, cooling and dehumidification, adiabatic saturation or evaporative cooling, and chemical dehumidification. Of course, we have seen one more process, that is mixing of air stream. So, we can apply mass balance and energy balance to find out the condition of air after mixing and the enthalpy of air. So, with this let me conclude lecture number 19. Thank you.
Hello and welcome to this piece of literary snippet. We usually know William Shakespeare as the most revered figure in the history of English literature. But we often tend to forget that he has also been one of the most hated figures in literature. And here I am not talking only about those boys and girls who have to memorize long sections from Macbeth or King Lear or Julius Caesar before they can go and sit for their school or college exams. But I am also talking about people who are themselves quite famous authors. Tolstoy, for instance, considered the writings of Shakespeare to be, and I quote, crude, immoral, vulgar, and senseless. George Bernard Shaw absolutely loathed Shakespeare, as he did Homer. But perhaps no other criticism about Shakespeare is more damaging than the one which says that Shakespeare is a marvelous storyteller, provided someone has told him the story earlier. Now, this piece of criticism is particularly damaging because it is true. None of Shakespeare's plays contain any original story whatsoever. They are all written using pre-existing materials, pre-existing stories. Now, does that diminish the stature of Shakespeare as a dramatist? Well, I'll leave that for you to decide. See you in the next episode of Literary Snippets.